he hates the UN. He loves the European Union. He loves democracy.
Okay, yeah.
And he hates Russia with a burning fiery vengeance for invading Ukraine.
Huh. Oh well, yeah. I don't really care for that part. But, yeah.
Anyway, I thought the resemblance was striking, and I couldn't keep quiet about it anymore.
Thanks for sharing. Okay, here we go. Our note. Let me open up what we were working on last time. One 7. All right, so we have F. Let me mute myself. So we have like 2 problems left on homework 3. A few people noticed that it was due yesterday. I'll shift due date till maybe like Tuesday, something like that, so we can get through the rest of our work and pop up chapter 3, because we're down here at 334. And these are the important things. We need a red balloon, right? If I could draw. All right, so we're back at it again. The theme of this module is all about equations of motion. And like from there, you can do a lot of stuff with equations of motion. Like in this last problem, we looked at equations of motion, figured out like normal force was was a function of velocity and the angle, and we could solve for that there. In the last one before that, we were looking at spring pendulum, and we could figure out like what are natural frequencies, like for bouncing versus swinging, are they related, this kind of thing. So there's a lot of stuff that we can do with equations of motion, but the first step, and this is usually the hardest step, and that's why I spend like an entire module just finding equations of motion, because that's the part that most people struggle with, even practicing engineers. Not exactly sure how to get there. Okay, so we're creating that equation of motion. This is kind of like the step-by-step of what we're going to do, of like A, B, C, D, E. So start off, here it tells us do a point mass model. Yeah, so let's make a point mass, kind of these 2 steps. What is the free body diagram of that point mass of a balloon? And then here, really this is part B. When you're choosing your coordinate system, you're implicitly creating your kinetic diagram, because your coordinate system is telling you what are the components of acceleration, and that's going to be F equals ma. Ma has 2 components. Let's do like, so try this out. Try drawing free body diagram and kinetic diagram. We're doing like ABC all at once. For a balloon, this is a balloon on a string. And I'll zoom out a little bit so you can see my red balloon, just one. We don't have 99. But with symmetry, it could be 99. So it could be like if someone bumped it, it was moving over to the right, and then as it comes back up, will it kind of stop or will it keep spinning? And that's kind of what we're trying to figure out here. What is the motion? How do we describe the one that pushes it up? That one, it is buoyancy because you're displacing air with helium. Yeah, I didn't think of that. Yeah. Yeah, so what do you want? What would be like rotation in the coordinate system? Yeah, cool. Yeah. And so like it's still like even with circular motion, it's still two vectors. They're still just kind of next to each other, whether they're rotating or kind of fixed in space. Did you already finish?
I tried to.
Okay.
I did my best last night. But I think this is probably
Okay.
from what I did last night, based on like stick with test lines and say, look,
Okay.
it's more my diagram here for tension on here.
Yep.
Then the weight force after this right cross strain.
Okay. Is it
Yeah, MG goes on because that other aside from the maximum like MG. So the opposite direction.
Neg diagrams equal to weight.
Only when you're driving because I always
Is acceleration always
well, of course. No, but I did. But in the question it says that the force, the buoyancy force is twice the weight. So then when you have this MG here, the buoyancy force for any direction, you would have how
So
so
when you have MG right there, MG cosine theta equals MG cosine theta.
yes, for the tension goes in here. This is tension
Or even or here, MG sine theta equals MG sine theta.
well, it doesn't mean about the parameter, but I think I just
Like we should end up with some kind of second given entropy equation. That was just like force.
You're right. You're right.
Yeah, so both these Oh, linear systems, that's like you start with the equation of motion, and then you go from there. That's linear systems. So it's the next step, like right after this. No, super easy, barely an inconvenience. Okay, so this is what I've seen. We got an mg, we got some kind of force of buoyancy, some kind of tension. Free body diagram, those are the main forces that I saw kind of drawn on there. So we'll get back to that in a second. Now, kinetic diagram, this is where I saw a lot of people freeze and didn't want to commit. Like, your paper won't judge you. It's your paper. You bought it. You can write whatever you want on there. Like, it's very much a judgment-free. Just try it. You can try whatever you want. But there's different options, but kinetic diagram is always based on what coordinates you choose. One way to do this is just like, I like Cartesian coordinates, I'm gonna use Cartesian coordinates. And I just, by God, I'm gonna have an MAX and I'm gonna have an MAY. And that's a totally valid way of doing dynamics. You could always try to jam circular problems into square coordinate systems. You end up doing a lot of like backend, like trying to get to the equation of motion is a lot of trig and a lot of trig identities, but it's not the end of the world. You can do that. Another equivalent way of looking at acceleration is in our polar coordinate system, where we have some kind of radial, like how fast it's moving away along that tension. So that one should be 0. It'll have centripetal acceleration, but the total acceleration outward's got to be 0, like r double dot. So we could call it like this, like MAR, and then I like to call it MA theta this way. But you could put it the other way if you, depending on what you want to call theta. If I call MA theta up and to the left positive, bless you. This is a negative theta. Like right now, it's some negative value. So as it moves up and to the left, it'll be increased. Like theta is increasing. So if it's accelerating that way, then velocity is increasing in that direction. How does that vibe so far? For the theta, like why? So I like to always do right hand rule positive theta, and so if I'm rotating like in the negative direction, then I have like a negative, like 0, I'm just calling 0 vertical. And then right now it's at like a negative theta direction. Yeah. Like we could have also said like, this is theta. It's catching up. The only difference there is that when we look at like what is equilibrium, like when would the balloon not move anywhere, it's at theta equals 90 instead of theta equals 0. So again, 6 of one, pi over 2 of another. I like this. But do it however you feel you want to do it. Whatever like speaks to you for your coordinate system. The heck is this thing asking for? Derive the inertial kinematics of the balloon. No idea? Kinematic diagram. Yeah, like our kinetic diagram. Okay, yeah. So it's got to have something to do with that, like our kinetic diagram, or yeah, because our kinetic diagram is the inertial, like m times our kinematics, right? Yeah, so something to do there. I like that direction. Yeah. Yeah, so it's asking it in like a fancy way, just using a lot of like $10 SAT words, but really it's just saying like, what in your coordinate system, what is acceleration? Because we want m times a, so we need some definition of a, and that's all we're asking for. Like, so we could cross all this out. What is ma? And just say like, what is our mass times acceleration? If you're forcing everything into that Cartesian square coordinate system, it's mass times second derivative of x and mass times second derivative y. Again, you'll end up doing a little more math, so I'm not going to do that. If you want to do it, you're welcome to. Just remember all your trig identities or look them up again. So instead, I'm going to focus like over here. And we already looked this up one time, so I'll scroll back up. I'm just scrolling up to where we like grabbed an image. It's in the textbook. It's everywhere that you look up like what is acceleration in a polar coordinate system. It's always the same equation. It's never different. Like if you're trying to describe things moving around circles, it's always this equation. So I'll write it down so we got it. So m times r double dot minus r theta dot squared. M a theta is m r theta double dot plus 2 r dot and theta dot. So that's the first step. Just that is our definition, right? That's just the definition in a polar coordinate system for acceleration. Do we know anything about theta or r? Yeah. L is constant, which concur, yeah. So r is always L, and derivative of L is 0 because it's a constant. All right, making progress. Love crossing out to 0. Do I know anything about theta? Like, what's the deal with that theta? Is that an important variable? Is that something that I need to like try to remove from my equation? What's the deal with theta? Is it changing? It is changing. What does it tell, if you know the angle theta, what does it tell you about the balloon? Like, do you know where the balloon is if you have the angle? If I tell you it's at a 45-degree angle, can you tell me how high off the ground it is? If you know the length of the string, right? So call it 1 meter. It's a 1 meter length string. Do you know how high off the ground it is for 45 degrees? I mean, we could figure it out, right? Like it's a fixed value. So this is that's like our main, when we talk about the degrees of freedom, it's our degree of freedom. Like that's what we need. If we know theta, and we know theta as a function of time, we don't need anything else. Like, I mean, we need constants to describe it, like what's L, what's G, what's the force of buoyancy, but in terms of like the motion of the system, theta is the main thing that we're trying to figure out. So we need that theta. So if that's your kind of chosen coordinate, that's what you're looking for. You're looking for an equation of motion that describes theta. What is theta double dot? What is theta dot? What is theta? Like, how are they related to each other? That's what we're trying to find. That's our equation of motion. So try it out. FMA. Write out these, so plug in what are the sum of the forces in your R direction, what are some of the forces in your theta direction. Try plugging those in and we'll see where we end up.
So can it differ because it's changing, if the angle is changing, then it changes at a certain rate while it's getting velocity. I'm trying to think of what that typically. Of theta. Yeah.
So we have, there's already a relation between
Oh, that's what. Oh, right, there's a focus. Okay. I'm used to it. Yeah. I'm just trying to think back to really early there were questions of what the ladder is looking at. It feels like something like that.
Those are like kind of similar, but a lot of times those are 0 degree of freedom problems where all of the motion is defined. This point, this mass, so if this point passes that mass.
Right.
Yeah, and buoyancy. I think in this case it's just 2 mg. You have 2 mg that way.
Yeah.
Oh, right, yeah. Yeah, because we do it pretty much. Yeah, if you only have one
Just for something like this.
All right, so I'm replacing FR and F theta. Is tension in the radial direction or the kind of twisting direction? Radial, right? So I'll put a negative T over here. I wrote negative because it's not, I can't apply tension to make the thing go away. So it's got to be a negative. Then buoyancy and gravity are always kind of opposing each other, right? So we could, what I could do is just say that this is 1 mg, because at least in this case, buoyancy is 2 mg. So if I take those two vectors, subtract one from the other, I have 1 mg kind of pointing up. How much of gravity is pulling the thing along the tension? Is it a sine theta or a cosine theta? Cosine? I like that. What makes you say cosine? Okay, yeah, yeah. So one way that I kind of gut check it is like if theta is 0, then it's vertical. It should be max, my max like buoyancy, kind of pulling it up, which makes sense. Cosine of 0 is 1, so my sine component would be 0. Yeah. And then do we have a positive mg sine theta or a negative? What do you think? Positive or negative? Negative? Maybe? Let's try it. Negative mg sine theta. Again, it's not judging me. It's just a computer or a piece of paper. All right, now let's plug in our other values. What's going to give me my equation of motion? That first one, the first equation, or the second equation? Second one? Down here, right? Oh yeah, we were supposed to put in an L, but that's all right. Negative G over R sine theta. How does that look? It's good? Yeah. Yeah. So use whatever angle you want, right? But in mine, I pick the same theta every time, and if it's a pendulum kind of problem, I always define it this same way. So this angle that's shown here is a negative theta, like it moves somewhere along that negative direction. So as I increase theta, I'm going back to 0, and if I keep increasing it, I'm going past 0.
So if you use that theta, would you have to you'd have to convert thetas when you go to polar units?
What do you mean convert theta?
Well, isn't polar starting from the horizontal going back, and then are the thetas different?
So the way that I drew it, like my coordinate system, if I want to talk about like x is r cosine theta, this is my x-axis. So it's describing height. But you're right, like if I want to say that the horizontal, that the floor is theta 0, I can do that, but now equilibrium is, yeah. And this is something, again, like every time I have something kind of swinging like this, like a pendulum, I always draw my x-axis along that equilibrium, like where I think it's going to sit. You can do it however you want though. Like this is just one way. It is the most common way to do it in most like physics and engineering kind of textbooks. There is a reason to do it this way, but there's also reasons to do it other ways. How are we doing on time? Oh, we got 10 minutes. What's the last one? 337? Yeah. Yeah. Where am I going? Where? That's our, so as far as like, what is the equation of motion? That's what we're looking for. Like, what is the differential equation? So that initial question, should it be positive, should it be negative? If this angle, if I push the balloon over to 45 degrees, just straight down, should I have a positive acceleration, like should it keep moving down, or should I have a negative acceleration where it moves back? Negative acceleration. What do you? So at least from an equation of motion, the negative sign makes sense, because if I have a positive angle, I have a negative acceleration. If I have a negative angle, I have a positive acceleration. So it seems right. At least it seems right to me that we did things the right way. Yeah. That could be, so that vertical of like theta equals 0, that's one, if you start there, then the thing won't move, because if theta is 0, sine of theta is 0, so acceleration 0. Oh, in reference, yeah, so theta is always describing, and again, describe theta wherever you want. You can put it anywhere you want. You could say that this is theta plus 360. It'll come back. It's a circle. But yeah, and then once we have that equation of motion, now we can think about things like, will this balloon ever stop moving? Yeah? Okay. Did we account for drag or friction? No. So will our balloon ever stop moving? No. It'll just keep oscillating. It'll look like a spring, right? Like if somebody moves it, it's going to move forever. At least in our model. And that might be enough. Like maybe that's all we want to figure out, is like what happens if that's the only forces acting on it. Or you might have a question about like, hey, it's going to slow down and it will come to a stop. How do I add that stopping power? Like, what's that going to look like? So drag would be one thing we could talk about, like how there's drag. I think that would be the main force kind of slowing us down. But here, and this is kind of a general truism, if your equation of motion only has acceleration and position, the thing's never going to stop moving, because everything is kinetic and potential energy, and you're just going to keep swapping back and forth between the two. Perpetual motion, yeah, we got it. All we need is a balloon and a string, and then it'll just go forever. Just no friction, yeah. Somebody suggested we should put it in a vacuum, so there's no drag. How much buoyancy is there in a vacuum? Not much, yeah. Yeah, you need something. You need to displace something to have buoyancy to push you up. Yeah. But it would reduce drag. You get 0 drag with a vacuum. You would also explode your balloon, because now even atmospheric pressure is now A lot of pressure, yeah. All right, let's take 5 minutes and then be done. It's Friday afternoon. Do 5 more minutes. We in it? No? I saw some head nods. Yeah. For tension? That is a great question. Like, can we assume tension is constant? Is tension constant? Yes, constant? Not constant?
It should be constant overall.
Overall constant? You think constant? We have an equation for it, right? I could say T is mg cosine theta. Or wait, what is it? A negative T. So over there. So in our case, is theta going to be constant? No, because at least based on our equation of motion, it's always going to be moving. So theta is always changing. So even this first term, we know tension has to be a function of time because it's a function of theta. We can make an approximation. We could go, all right, cosine theta is basically 1. So maybe there's always an mg. So that if we're doing a linearization of it, we could say roughly mg is always there. What about theta dot squared? If theta is changing, is the velocity constant? No? That one's kind of tricky. We don't have an answer for like what is theta. We know theta is a function of time. Roughly it's going to oscillate, right? So if we take a derivative of like a sine wave, what do you get? A cosine wave. Take another derivative, you're back to another sine wave. So that theta dot squared is also a function of time. So both of these are saying like tension is not constant. We can solve, like we can, if you had tension like in some other equation, you can plug in these values and say, this is tension. Yeah, solve for theta dot squared, whatever we want to do. But awesome. That was a great question. Let's just mic drop on it. Be done for the day. It's Friday. It's so nice outside. Get outside, go hiking, do something. Get off campus or walk around campus. Campus is beautiful right now. Be outside, get some fresh air. And then we'll come back Monday, do one more problem, and then Tuesday we can turn in the rest of this. Thanks a lot. I'll change the due date. Yeah, there's no late penalties in general anyway, but I'll change the due date just so it doesn't say like everything's late.
So if I just redid what I did last night with the new stuff we did in class, we'll be fine?
That's fine.
All right,
Yeah.
great.
Yeah.
Thank you.
Great. Thanks a lot, Miguel.